Uh, so, let's start our lecture. Our in the previous session, we have completed angular momentum thing and its conservation. Now we are going to start our today's concept, that is recall our concept. So there is a question on your screen. You need to answer that question. Have a look at the question. Am I audible? You can answer that. Yes, sir. Thank you, JNV Daman. So I think that was the question that I have given you in the homework in the last session. So there is a uniform rod. First of all, just tell me how many of you attempted this question given in the homework. If you have attempted that, then I will leave it as a homework and moving forward. I will move forward if you have attempted the question, because it will take another 5 or 10 minutes actually. Okay, so I think I just have to leave it because it was your homework actually. So today's topic is kinetic energy of a rotating body. Just think about it. Let's suppose there is a rigid body, and this rigid body is rotating about an axis like this. This is the axis of rotation. What I am saying, let's suppose this angular velocity is omega, and what we have learned that if I consider a particle here, let's suppose the particle is P. This particle will be moving in a circular path like this. If I suppose that this is particle number one, particle number two, we can take a lot of particles here. Let's suppose this is ith number particle having mass mi and its radius is ri. Then the total kinetic energy of the body can be written as kinetic sum of kinetic energy of all the bodies. Sum of kinetic energy of all the particles. Now, if I say kinetic energy of this ith particle is, you will say half mass is I mi vi square. This is the kinetic energy of ith particle. Now, again, if I say that vi is the linear velocity, can you transform it? Half mi, and what we know that v is equals to r omega. Is it clear? Then vi will be ri into omega. I am replacing it. After squaring, it will become ri square omega square. This is the kinetic energy of ith particle. If I take total kinetic energy, it will be k is equals to, if I add all these terms, it will become sigma half mi ri square. And what you can say, this half mi ri square is what? Half is constant, we can take it out. And mi ri square is what? Moment of inertia. So it will become k is equals to half I omega square. That's it. Uh, you can take a screenshot of this portion.
No, no, but
Okay. So I think this is clear to you all. Okay. So moving further, now we are going to discuss about combined rotational and translational motion. This is again a most important topic of the rotational motion. We look at that. What is combined rotational motion and translational motion? Suppose the body is moving linearly in a straight line with some velocity v. This is translational motion, and this is rotational motion. If we add them both, it will become combined motion. So just suppose that the body is moving with a constant velocity v, and it is rotating with a angular velocity omega at some time. Now focus few points. Let's suppose this is the center, this is point A, and this is point B. Again, this is center, this is point A, this is point B. As we all know that if a body is rotating, then these points A and B will linear velocity. That linear velocity will be, we will say V equals to R omega. That linear velocity is V equals to R omega. If I talk about point A, it will have a R omega velocity in this direction. Point B will have a velocity R omega in this direction. What will be the velocity of point C then? The velocity of point C will be zero because this is the point about which the wheel is rotating. So it will remain at rest. This is the axis point. Will remain at rest. So these are the velocities of A and B. Now, if I add these two motions, then what you can see that point B will have two velocities, one due to rotational motion, one due to translational motion, and both velocities are in the same direction. So the net velocity of point A will add according to the vector rules. So it will become V plus R omega. And if I talk about point B, the net velocity will be one is V in the right side and another is R omega. So net velocity will be V minus R omega. So that's what the combined translational and rotational motion in which velocities add according to the vector rule. We have to consider translational motion separately and rotational motion as on a separate basis. So these are the two basic points, that this is point A is the topmost point, point B is the bottommost point. What if I talk about some another point? Let's talk about this point. Suppose this is point B. When the body is moving in the horizontal direction or in the x direction linearly, then this point will have a velocity. This is a rigid body. All the points will have same velocity v. But at this point, due to the rotation, the velocity will be tangential, r omega. So can you add these two velocities in the combined motion? One is along horizontal x direction, another is along y direction. Can you add these two velocities? You know the formula to be used here. Yes, they will be added by parallelogram rule of vector addition. That parallelogram rule of vector addition says under root a square, or you can write it here. The resultant will be in this direction. The resultant V will be under root E square plus R square omega square. Can you see the angle between these two velocities is 90 degree? So cos 90 will be 0. So I am not going to write that term further because cos 90 is 0. So this is the velocity of point D. I think just tell me whether the written thing is visible to you or not. Let's just stay here for a minute and just tell me whether it's visible to you. There might be some issue with the handwriting because of the kind of motion I am in. Okay. Moving further. So now there is a rolling motion thing. What is rolling motion, or what is the difference between combined rotational and translational motion and the rolling motion? Let me explain it to you. When I say combined rotation and translational motion, there may be a situation when the body is sliding as well. Like assume a situation when you start a lot of higher velocities. When you start the car at higher velocity, sometimes you can see that the wheel of the car leaves a black mark behind. That's usually the slipping of the wheel. I think many of you have seen this in case of bike or in case of four wheelers as well. So that is the case of combined rotational and translational motion. When there is a slipping between body and the wheel, body and the surface. Now, when we talk about rolling motion, what is rolling motion? The combined motion in which there is no slipping at the point of contact. Can you see the point of contact? This is point of contact A. If the velocity of point of contact is zero, then this is known as rolling motion. It has translational motion, it has rotational motion, but the important thing is the point of contact always remains at rest with respect to the surface of the body, sir, at which it is moving. So main thing is no slipping, or you can say velocity of point of contact is the important condition. Now, can you identify the velocity of point of contact? Let's suppose the wheel has the translational motion of velocity v and the angular velocity omega. Can you say that all the particles of the body are moving in translational motion with the velocity vcm? Vcm is the velocity of center of mass. There will be a rotational, the will be r omega, linear velocity vcm. So the net velocity of the point A VCM minus R omega. So for rolling motion, this point of contact has no velocity. So what is the value of VCM? That is equals to R omega. This is another very important relation that in rolling motion, center of mass moves with the same velocity as the point of contact in the backward direction. If it was considered a pure rotation, we rolling motion.